Hit record. Record the audio. Color chart. Audio and video, says Kim Barron. Hey, Zafan, sorry about the switcheroo there. So what happened was this. So this is my new telescope mount. So it's a ZWO AM5 mount and a color camera. And I was, we had clear sky, perfect clear skies, except we had a full moon, but I'm trying to test the new smart telescope setup. And so I had to do that instead of doing the live stream. And then tonight I will probably do the same, and I will probably try to stream the eclipse, because why not? I think I can pull it off. Yes, I think I can pull it off. I'm just sort of thinking about the tech stack that we require. I'm not 100% there, but I will. So yeah. Okay, so the way this goes, yeah, we'll talk about my DVD collection in a second, but we're gonna sort of officially start the video right here, and then we'll go into the rest of it. So here we go. Benjamin Beardless, 39 meters across. It took a second for that to register. 39 fecking meters. So this is response to the extremely large telescope, which is currently under construction in Chile. And it is the primary mirror, like the big mirror on this telescope, is 39 meters across. And that's really big. Like, it's really, really big. And it's hard to sort of give you an idea for context. And so, like, think about just like a regular big telescope mirror that you might see in, say, Vera Rubin or the Very Large Telescope. You know, the Very Large telescopes are 8.1 meters. Vera Rubin, roughly the same size. The Keck Observatory is 10 meters across, right? So for those of you that don't speak metric, that's 30 feet. You probably don't have a room in your house that would fit a mirror that big. They're very, very big. But that is nothing compared to the size of the extremely large telescope. 39 meters across. That is longer. You know, a blue whale could sit inside the 39 meter telescope in the extremely large telescope, and with room to spare. That's like, I don't know, like half the width of a football field. It is, you could sit a 737 jet on top of the primary mirror of the extremely large telescope. It is very, very big. These things are gigantic, and that's what it's going to take to be able to do the next generation of astronomy with these big observatories. And the crazy part is that the extremely large telescope was not the biggest version that they were considering. So when they were in the planning process for the extremely large telescope, they were considering an even bigger version called the overwhelmingly large telescope. And at this point, I'm sure we'll see an XKCD comic that makes a joke about the size of telescope names, makes a joke about the names of telescope sizes. But yeah, and so they were planning the overwhelmingly large telescope, and that was going to be 100 meters across, right? So like the length of a 100-meter dash. And it was sort of like considered to be the largest feasible possible telescope that you could build on Earth. That it would have just this enormous, almost spherical superstructure around the telescope with trusses just to stop the thing from warping and bending. And it would just be an astonishing piece of astronomy kit. And unfortunately, they went with the 39-meter version, but maybe at some point in the future. I've even seen some cool proposals about putting, say, the 100-meter telescope on the moon, where you've got lower gravity, so you don't need as much superstructure to be able to make a telescope that big. And then just imagine what we would be able to see with a 100-meter telescope in space. But yeah, this thing is big. I mean, now that we're in the age of Vera Rubin, and now I can stop being excited and looking forward to Vera Rubin, it is time to now start being excited and looking forward to the Extremely Large Telescope, which is still just a couple of years away. Okay. I forgot to press that button. Okay, well, we're back. Okay, so, hey everybody, welcome to the live question show. This is the thing we do every Monday. The time rotates, so sometimes it's 5 p.m. Pacific, sometimes it's 8 a.m. Pacific, which is 5 o'clock-ish in the early evening in Europe, and then sometimes it's 10 p.m. Pacific time. I really should say all these times in UTC, in Universal Time, but you know the conversions just break my brain. Although, apparently, we've got daylight savings time switchover that is happening on March 8th, so next weekend. And in British Columbia, that will be the last time we ever switch. We will remain on daylight savings time forever. That we are no longer going to switch back. We are off the hamster wheel of switching on and switching off. And it's not my preference. I would prefer standard time. I'm a morning person. I would like to have more light in the morning, and so before I would have half my year have the morning and then half my year I would have the evening lighter. But I think I would prefer to have the mornings that I don't want over having to switch back and forth. Like some people just want to watch the world burn. I'm one of them. So daylight savings time can be gone for British Columbia. The rest of you suckers out there, you're still going to have to switch back and forth, but we are free of daylight savings time. Right. So go ahead and put any questions that you have about space and or astronomy or whatever into the YouTube comments, and I will be watching the feed, and I will grab those questions and I will highlight them and feature them, and I will answer them. Now this is the raw material. This is the grist for the mill that is our edited question shows. And I actually got a comment from someone. I don't know if I mentioned this before. Someone said the live stream is too slow, that you should have somebody like prepare the questions for you, and so you can spend less time looking around for the next question. And that, of course, is a very difficult suggestion, because how will that person know which questions I want to answer? Right? Like I can't. So I have streamlined the process as much as I can to be able to answer the questions as quickly as I can with as little fluff as possible. I don't even look at chat. I only look at your filtered, edited questions. And yet it is still too slow for some of us. Like, I know you're probably just watching this while you're also on your phone, and you're also watching Netflix, and you're also playing a video game, and you're also spending time with your family. And this is just one more noise in the background. So, some ground rules. Speaking of totally being distracted, keep in mind that I am a journalist, not a scientist. So if you want my scientific opinion about various concepts in space or astronomy, I cannot provide them to you. I can merely parrot the scientific consensus. And if that bothers you, watching this video is not required. You can freely choose to watch it or not watch it. And go watch some other channel where people will do their own research and come up with their own opinions about space and astronomy. I try to give emphasis to the people who've never had their questions answered before. So, if this is the first time, if you're like finally worked up the bravery to ask a question, then I will try to give emphasis. And then the other thing is that, we get a lot of the same questions. So, if it feels like it's a question we've answered a lot, I might just skip it. Or if I don't know the answer, I might just skip it. Or I might just skip it. And I don't need to justify it. I will never explain it. It will be a mystery to you and to me. All right. Let's get started. Alan M. Gross asks, what time does the lunar eclipse start tonight? So, it depends on your time zone. So the best thing to do is just Google it. So when I Google lunar eclipse time Vancouver, which is kind of close to me, then I get a bunch of things, and one of them says the one on March 3rd, Local time, it begins at 12:44 a.m. The maximum is at 3:33 a.m. Did I say that I wanted to live stream this? 3:33 a.m. And then it ends at 6:23 a.m. So, yeah, that's for me, Pacific time. It's 3:33 a.m. March 3rd. But so just Google it, and you should find your local time. And this is like going to be one of the last, like really nice total lunar eclipses visible from the Pacific region. So if you are into it, set an alarm and get up. That's what I'm going to do. Okay. Jack Seabranch. Given what we know about the solar system surrounding us, which is the closest one that might contain intelligent life? So, we only know of a fraction. We only know a very little bit about the close star systems to us. Within about 10 light years, there are only about 10 star systems. And then once you get to 100 star light years, then there's like 1,000. And then once you get to 1,000, then there's like 10 million. So there's like a lot of stars as you get out to that kind of 1,000 light year range. And we've only detected planets merely around about, say, 5,000 stars. There's a bunch of planetary systems. And you need a very special set of circumstances for us to be able to even detect the presence of planets around that star. They need to essentially be lined up so that the planets are passing in front of the star from our perspective. There's some other ways you can detect planets, but that's the main way. And the good ones, so the TRAPPIST-1 system, K2-18b, there's a couple of other star systems where you've got an Earth-sized world orbiting around a red dwarf star. Those are interesting targets merely just because they have Earth-sized worlds, and that's like the first step. And some of them are in the habitable zone. Like that's the second step. So there have been searches with radio telescopes to scan those worlds. And in fact, there was one, some SETI astronomers, so searching for extraterrestrials, they recently used the Very Large Array, which is the big radio telescopes in the US, as well as the Meerkat Observatory, which is in South America. And they scanned K2-18b, which is this weird this weird Haitian or potential Haitian world where you've got this thick planet with a sort of a thick ocean of water surrounded by this hydrogen atmosphere. And they didn't detect any signals. And there's been a lot of work by the SETI community to try and scan various things for signals. Like they scanned Oumuamua, they scanned 3i Atlas, they've scanned a lot of other planetary systems that they can see. And so far, none of them have turned up. Now, the most interesting worlds to scan are going to be the ones that are more Earth-like. So you want to look for an Earth-sized world orbiting around a sun-like star. You want to look for an Earth-like world orbiting around a orange star. But so far we don't have the technology to be able to do that. We need the extremely large telescope to come online, or the upcoming Habitable Worlds Observatory to be able to image those. And so for now, we don't really even know the good targets to scan for signals for aliens. We just have to do this kind of blind search. And there are, like I said, millions of stars within 1,000 light years of us. So it's a big search space. And then you consider all of the frequencies across the radio spectrum that those extraterrestrials could be, broadcasting in our direction on. So we've only just started to look, and we're only just examining a fraction so far. And we don't even know what are the best targets yet, because we haven't done an accurate survey of which systems have stars and which systems have, we haven't done an accurate survey of which systems have planets in the habitable zone. We just don't know the answers to these questions yet. It's too early. Vista Tutti, are the rebel provinces like Alberta and Quebec also going DST? I don't know about Quebec, but apparently Alberta is not. So they're on mountain time, and and there's some parts of British Columbia that are on mountain time, and they're gonna follow the DST DT. Or, they're gonna go with Mountain Standard Time and Mountain Daylight Time. So they're gonna keep switching back and forth. And I don't know what Quebec is gonna do, but I think it's just right now it's just British Columbia. And originally, we had wanted to do this in British Columbia for a couple of years now, and we were waiting for the rest of the Cascadia states to join us. So the plan was that I think everywhere from Alaska, British Columbia, Washington, Oregon, California, we would all do the switch, and then we would all stay on the one or the other. And I guess we got a little sick of waiting on the other states, and so we just said we're going for it. So yeah, so try to keep up, Western U.S. I like turtles. Would you be willing to live on a lunar base for some years? No, I don't think so. Like, I would be willing to travel to a lunar base and spend a week there, maybe a month, and then I would like to come home. And like, I think I would just get bored. I don't know. Have you ever been on a cruise ship? You get on a cruise ship and you just like, this is amazing. Like, there's food everywhere you want, and you just sit around, and there's like movie theaters and libraries and games rooms, and you can work out, and you can hang out with your friends. And then day 2, you're like, oh, this is still too much. And then by day 7, I'm like, I can't wait to get off the boat. Excuse me. Yeah. We don't breathe water, he says, drinking more water. Okay. So I kind of feel like going to a lunar base would be a little bit of that. In the beginning, you would just be amazed. The feeling of the less gravity, looking out the window to the stark lunar landscape, just knowing in your mind that you're on the moon, standing out and looking at Earth hovering in the sky, looking at how clear and perfect the night sky is, using the telescopes at the station to be able to observe objects with a level of clarity that you just can't, performing a bunch of interesting science experiments. And then you would start to normalize, and then you'd start to miss things of home. And so I think probably like a week, 2 weeks, maybe a month at the most, and you'd be starting to have had enough, and you're going to want to come home. There's also the concern of just being exposed to all that radiation. If you're on the surface of the moon and you're not protected by a meter of regolith, then you're going to be taking a dose of radiation. It's about 200 times what you experience on the surface of the Earth. And so you're increasing your chances of getting cancer. And at a certain point, you're going to feel unnerved. You'll be like, oh, I've had enough. I want to go home now. So my guess, knowing myself, I'd probably hit that at the 2-week mark. Dr. Zab, if neutrinos travel slightly below the speed of light and a supernova is light years away, how can neutrinos from the explosion be detected hours before the light becomes visible? Yeah, so one of the cool ideas is that if you want some kind of advance warning of when a supernova is going to happen, then you look for a flash of neutrinos. And they will be ahead of the supernova by a couple of hours, maybe even a couple of minutes. And so there's this thing called the Supernova Early Warning Network. And this is a network of neutrino detectors on Earth waiting for that flash of neutrinos. And when they detect it, they will figure out where it originated. They will inform the big observatories on Earth. They'll be able to point their telescopes, and then they will watch the supernova happen. The network will only work within a few 100, maybe 1,000 light years of Earth. So Betelgeuse would set it off. But people have proposed ideas that could expand the network all the way out to the size of the Milky Way. And so you would have this network, this warning of when a supernova is about to go off. And so the question you ask is, like, neutrinos go slower than the speed of light, right? They have mass, so they can't go the speed of light. And so how do they get to us first? And the answer is that they are able to escape the collapsing star faster than the radiation does. So one of the interesting things about neutrinos is that they can pass through matter unaffected. You are currently experiencing trillions of neutrinos going through your body from the sun after they already went through the Earth, right? They went through the sun, like they were generated at the center of the sun. They went through the entire mass of the sun. Then they went through the Earth, and now they're going through your body, and now they're heading off into space, and they will probably not be stopped by anything. And it's only when you have a gigantic volume of water that you are sending countless neutrinos through it that occasionally one will slam into a molecule of water and release this cascade of particles that you detect it. And so that same idea that they're getting out of the sun, they're getting out. So the supernova is happening. The star is imploding. It's piling up material at the center. And in fact, it really kind of looks like now the neutrinos drive whether or not you're going to get a supernova or whether you're going to get a direct collapse. So if there's enough neutrinos being generated inside the center of the star as it's imploding, then they can, and again, they barely connect with anything, and yet they are still an outward force that causes the star to explode. Instead of just going, just wrapping up into itself into a black hole. And so the neutrinos just escape, while the radiation has to make its way through all of this infalling material. And that takes minutes, if not hours, for it to be able to happen. And so the neutrinos have a head start. And they are traveling slower than the speed of light, but not much slower. Like they're traveling, 99 point, I don't know how many nines, the speed of light. And so they are almost going the speed of light. And that's enough for them to be able to get that edge and to be able to get out. Again, neutrinos can go through a light year of lead, no problem. So, they're just not stopped by the imploding star in the way that the radiation does get stopped. Use toaster. What are we talking about today, folks? Are the aliens finally here? Hey, whatever happened to the disclosure announcement that was going to happen last week? I guess there's like a bigger distraction is now unfolding. And so all eyes are off the potential alien disclosure. Apparently on one of the prediction markets, you can bet for or against the alien disclosure. And my prediction, although I'm not going to put my money on it, mostly because I don't like people betting on prediction markets, is nothing's going to happen. Nothing. We will see no solid evidence of aliens visiting Earth. And because there never has been, that you can't have conspiracies that complicated. So there would be other evidence that would have shown up in all of the observatories that are scanning the sky. All of the people who are holding cell phone cameras would be detecting things, and we just haven't. So, the aliens are not here yet, but we're looking for them. We'll wait for them. We're ready. And Skeptic Y2, why do galaxies 1 billion light years away look the same size as a galaxy 50 million light years away when a big telescope takes a picture with them in the same field of view? I mean, when you see a picture of a galaxy, you don't know how much of the field of view of the telescope you are actually seeing. So the biggest telescopes have really huge CMOS sensors, like the camera that is capturing the image is enormous. The one in the telescope behind me is a 3,000 by 3,000 pixel CMOS. and Vera Rubin is 4.3 gigapixels. I forget what it is. It's like 40,000 by, anyway, it's like tens of thousands pixels across. And so, and it has this really wide field of view. And then it will take an image, and some number of the pixels on that telescope will have the image of the galaxy on it. And then the astronomers will crop into that part of the image to be able to display it on news releases, but also to study it for the science. And so you have no idea what was the field of view of the telescope. This telescope has about a half-degree field of view, so it's like a little bit bigger than the moon, like maybe twice as big as the moon, actually. 0.56. Anyway, it's bigger than the moon. But others, for example, say James Webb or even the Hubble Space Telescope, are a fraction of the moon. They can only see this tiny little postage stamp version of the sky, while Vera Rubin has this gigantic wide view. I forget exactly how many. I should get all this in my brain. It has a very wide field of view, many moons across. And so all of the factors are the size of the aperture, the field of view of the telescope, the speed of the telescope, the size of the sensor that the images are being captured onto, and then the final crop that the people do. Like, they literally take the image and they crop into the part that they want, and they copy paste it and they put it into whatever they need. And it's funny to me when people say, like, when you see the images of the astronauts and then you see the moon, or when you just look at pictures when you see the astronauts on the moon and you see pictures of the Earth, people make some kind of judgment about how big the Earth is from the picture. But you can't make any judgment about the size of things taken by a picture, because it all depends on the lens. If you have a wide angle lens, then things look small. If you have a telephoto lens, then things look big. If you crop in, if you have a big sensor on your telescope or on your camera, then you can zoom in on that little part and reveal that. So it's sort of like not a reasonable thing to sort of argue about. But in your case, yeah, the size of the objects have many different factors. And so, you can see that they start to look bad, right, when they're really far away and you're not able to make out really nice spiral arms. But generally, when you look at a picture of a galaxy taken by Hubble or James Webb or whatever, if you can see the spiral arms and there's like a lot of structure and you can see little knots of star formation and the galaxy looks really cool, then it's in the tens of millions of light years range, right? Out to 200 million, 300 million light years away. If the galaxy clearly has a spiral shape, but all you can really see are sort of large scale features of it, then you're in the hundreds of millions to a couple of billion light years away range. And if you can you have a hard time telling whether it's a spiral galaxy or not, then you're out to 5 billion, 8 billion, 10 billion light years away. It's the quality of the resolution of the image that will be your sign for how far away that galaxy is. FL photo catcher. Why does telescope interferometry need to combine the light from telescopes that arrived at the same instant to work? If the object image wasn't changing so much, I don't see why it wouldn't work. So the trick with an interferometer is that it allows telescopes that are separated with nothing in between them to act as if they are a telescope the size of their separation. So in other words, you have two telescopes, they are a kilometer apart, and they are looking at the same target. Then it is as if you had a telescope that was 1 kilometer across. Imagine you have a telescope that is 1 kilometer across. That's a very big telescope. And that allows you to get, essentially allows you to have resolution. So you can pick out features that are very small. The resolution that you have is of a telescope that is as big as 1 kilometer across. What you don't get is the sensitivity. So you don't get to see faint things. You have to see bright things. But if you have, say, two stars that are orbiting around each other and the stars are very bright, you take your telescope and you look at the stars and you can't tell that the stars are separate, and then you take two telescopes and you put them side by side and you move them apart. Eventually you'll get to a point where you can actually tell that it's two separate stars that are orbiting around each other, and that is interferometry. And so people always ask, like, could we just take the world's telescopes and add them together and to make one big telescope? And the problem is that it doesn't work. That they need to be on the exact same wavelength, and that's the thing that you were mentioning in your question. And so, a way to sort of think about this is that this is how a regular telescope works. Like, a regular telescope lens is an interferometer, in that you have wavelengths of light that are coming from distant objects. Photons are coming from distant objects, and then they are hitting the lens of the telescope at the exact same time, or within the nanometer give that they require. And then they are bouncing off of the mirror, and then they're being focused into whatever instrument you're using, or your eye. Or your eye. And so, and that is, if you want the baseline, if you want the resolution, then it has to be the same. It has to be the same wavelength. It has to be essentially the same photon. And so this is why for the Event Horizon Telescope, which is this network of telescopes around the world, they were using radio waves, because radio waves are giant, right? Radio waves can be tens of centimeters, a meter across. And with that, you can use atomic clocks. You know exactly when the radio waves were collected with your atomic clocks. And then on computer, you can then do the interferometry. You can mash them together after the fact. But if you're using very narrow wavelengths like visible light, like ultraviolet, like infrared, you have to do this in real time. And so you actually have to have some mechanism that makes sure that you're getting exactly the same photons. Now, you can combine the light from several telescopes, and that will give you more sensitivity. So in other words, if you had two identical telescopes side by side, and you were okay with them not receiving their photons at exactly the same time, then you would just have the equivalent of the two telescopes. You had 1,000 telescopes, you have the equivalent of 1,000 telescopes, but you don't get that resolution, that baseline, that ability to pick out features on the surface of stars really far away until you build the interferometer. And that's why the Chara array, I've done an interview on the Chara array, the telescopes themselves are fairly modest. They are meter telescopes, couple of meter telescopes, but they're separated by hundreds of meters. And they are aligned in this really complicated way, so that they have carts that move back and forth. As the object that they're tracking is moving through the sky, the distance that the light goes to get to the different telescopes changes. And so they have to have these carts that move back and forth to make sure that the telescopes are still aligned again. And they can see features on the surfaces of stars. They can pick out stars that are orbiting around each other. It's an incredible technology, but you've got to get down to that level of precision. And when you think about the wavelengths, right, of visible light, they are in the hundreds of nanometers. Like, that is a tricky measurement to be able to make. RP1 for breakfast. Is Mars flat too? Mars is as flat as the Earth is. Oh, maybe it's less flat, because the Earth is a flattened ball. An oblate spheroid. One of a mine rocks. Are they going to rip the ocean bottom up for dollars? Isn't that our real future, the vast unexplored seas? So I think the thing you're talking about is these sort of mineral concentrations that have been found at the bottom of the ocean. And these have been made over vast periods of time, like millions of years, when you've got this mineralization that is building these little balls of minerals. And there's really valuable minerals in these things. And so they're nodules. And so people are proposing that you just put drifting it down on the bottom of the ocean, and you drag it along, and you will pick up all of these things, and then you can refine them down to use them. And it's probably going to happen at this point. And yes, it is probably going to cause damage to the ecosystems that are there. Although at the very depths of the ocean, the kinds of ecosystems that are there are different than than the ecosystems that you would find near the coastlines. But they're, in many cases, they're unexplored. Like we have no idea what lives there. We have not spent any time exploring them. But our world runs on money, and so this is a potentially easier source of money out there. The problem is that nobody owns the ocean floor, and so people are trying to come up with ways to split the revenue on these things. So it's like a one-time access to minerals that have been concentrated. It will cause unknown damage to the seafloor if you just go after them in a very drift net fashion, which they will, of course. I don't think it's a good idea for a bunch of reasons, but there's money to be made. Ilyakurakin. Do they still make DVDs? So I should explain this. So this is my DVD collection, and about 4 months ago, I was trying to watch a movie series on Netflix or Prime or Disney or Crave, or one of them. And I forget which one it was, but it had just been, I remember. That's right. So my wife was watching Star Trek Voyager, and there was this warning on Netflix that they were going to remove Star Trek Voyager in 5 days because they're all going over to Paramount Plus. So now we're going to chase them over to Paramount Plus. And she was like so mad, and I was getting really mad. I'm like, we don't own our media anymore. And so then I was down at one of my local thrift stores and looking in the DVD section because I was starting to wonder, like, why should I own my media? And they're so cheap. So I'm like picking up DVDs for $2 or $3. Blu-rays are more like $5. And I then sat down and made a list of my 100 favorite movies of all time. And I found most of them. It's kind of amazing. And so I have been slowly, or maybe kind of quickly, just rebuilding a collection of all of my favorite movies. And now every night, my wife and I will watch one movie. We watch the original, the Lord of the Rings extended editions, or we watch the Matrix series, or we watch the Conan series. So we watch a bunch of movies, and I love it. So, I've become a media collector, and I'm a person who hates atoms. Like, I really hate collecting things. And I actually very happy and kind of obsessed with collecting DVDs. So I've got one shelf right now, and then I actually ordered 2 shelves, and then my wife stole one of them. So I've got another version of the shelf coming, and then the plan is I'll have these 2 shelves side by side, all of my favorite movies and TV shows available to me forever. And we're going to cut off the streaming services. And it's kind of amazing. I did the math that the amount that we pay on streaming services, it would take about 5 months to pay for the entire collection of DVDs and Blu-rays that I've collected together so far. But there are holes. And so it's all like, if you want older stuff from the 80s to the 2015 or so, it's very easy. It's like, don't buy anything new. You just buy it all used at various thrift stores. But then later than that, it's actually kind of hard to get them. And so I have broken down and bought some stuff on sale from Amazon, stuff that's newer, to fill gaps in the collection. But the vast majority of this is garage sales, thrift stores, pawn shops. I'm having a lot of fun with it. So yeah, they still make them. And I have a 4K player, but I found that I actually am just better with I prefer the Blu-ray. The 4K is kind of finicky, and I have a real hard time distinguishing the difference on a gigantic television between the Blu-ray and the and the 4K, and there's been problems with the 4K where it's, you know, because it's so or the size of the rings, the memory compaction on the 4K Blu-rays, it's so tight that it's, you know, it's kind of a not as durable medium. And so Blu-ray sort of, for me, feels like the sweet spot in between. But DVDs look fine. I mean, they look definitely low res, but they're fine. I wouldn't buy a DVD new, but I'll pick one up used. And then I swap them out. So as I find the Blu-ray, I swap out the DVD, I give it to the kids, and now I have the Blu-ray version of it. And I will be posting my top 100 movies, or top 100 speculative fiction movies of all time, over on Patreon at some point. I have the list, I just haven't published it yet. Sean Roberts is saying, I have the 55 QLED 4Ks do pop. Yeah, we've got the 60-inch version of the LG, and I think it's the QLED. It's a really nice TV. And we played the Dune movies on it, and it was great. But I got Blade Runner 2049, and I got the Lord of the Rings series on 4K. But I haven't really wanted to invest in 4K. Tie balls. There you go. Tie balls. I remember you mentioning seeing space books with excellent pictures that sparked your curiosity for astronomy. Were they the Time Life Voyage Through the Universe series? Do you still have them? So they weren't the Time Life Voyage. I think it was Time Life Our Universe. No, it was Our Universe. Book. Our National Geographic, Our Universe. And I ordered a secondhand copy of it from someone on Amazon, and it never arrived. So no, I haven't got a copy of the book, but I will, now that I'm getting nostalgic. If I've broken down and purchased a bunch of DVDs, the very least I can do is break down and actually buy the most influential book that got me interested in astronomy. Jimmy James, is one of those favorite movies The Black Hole by Disney? Absolutely not. That movie is terrible. Billions and billions of stars. Will you be checking out the lunar eclipse tonight? Yeah, probably. I'll probably live stream it. So I've got the telescope set up now. I've been doing a lot of work to make it track, and so I'm going to see if we can make it work tonight. So I'll keep you posted. Light dark. What scope did you buy for your astronomy setup? So I'll grab the telescope. So I might have mentioned last week that I'm in the process of building my own smart telescope. And you'll get a chance to witness it in a couple of days when I do some live streaming with the telescope. But the gist is that I've coded up, thanks to Claude Code, my own custom interface that mimics the same things as a smart telescope. So you put the thing outside, you turn it on, you have it look at a spot in the sky, you plate solve the sky, and now the telescope knows what it's looking at. And then I've got an interface that's got a live feed to the mount and the camera. That's the camera there. And it's bringing them in. And so then I have a big database of all of the astronomical objects, and I can click on the objects. I also have a database of, objects in the solar system, comets that are visible, the moon, things like that. And then it will automatically slew to that target. And then it will bring up the object in a live view. So it's sort of being refreshed. And then I click stack, and then it starts building up the image frame by frame by frame for as long as we want. And then it saves the final stacked image to a directory that I'll make available to all of you so that you can just download the image as we do this. And so it goes very fast. It's very cool. And so it's the reason why I didn't do the live stream last night was because I had clear skies and I had to get some more testing done while I had clear skies. And I was hoping to live stream last night, but it just was too buggy and it wasn't ready to go. So I should be ready tonight. So it's a ZWO A5 mount, and then it's an ASI ZWO ASI color camera. I forget the exact number on it. And then the actual telescope is the telescope that I've had for a long time. So this is a Stellar View 70 millimeter refractor. And I've had this for 10 years. And so I just use this telescope. So you'll probably see this telescope a lot, or see the images from it tonight. And so, there you go. Put that away. All right. Yeah. So it was about 2,500 Canadian for the mount, and it was about $1,000 for the camera, and I already had the telescope. But the telescope is, let's say, $600. And then I have a Raspberry Pi that controls the whole thing that's been coded. So. Moon Trustee, Fraser's doing AI coding right now. So do you see this? Right? This is from AI coding. Yeah. I'm using Claude Code. I've got a whole bunch of apps that I built. We actually published the entire Universe Today website with a content management system that I designed and built with Claude Code. I've got the smart telescope thing that we built. I've got an interface that I'm using right now to be able to do this live stream with you. So it handles the questions, puts them up on the screen. I can put pictures up. So that's all being done with AI coding tools. And I've got a whole bunch of other stuff that are just like personal productivity stuff that we've got a whole sort of way of looking for duplicate stories for the writers so they all can kind of work together while they're working on stories that we've built. So yeah. I mean, like, this is why I'm like so ambivalent about AI, that on the one hand, there's all kinds of interesting, very productive, useful things you can do with it. And then on the other hand, there's all kinds of really negative consequences that are happening already, that will happen shortly, that can happen to all of society. And that I think right now it's all hot takes, which makes me sad, because there are certain things that are terrible with AI, like making AI slop videos, using AI to do your school homework, using AI to make decisions about employment, and making music with it. All right. And then other thing I think is, it's doing math, helping with science. I think there's a lot of stuff that it could be very useful for. And we are just either AI bad or AI good. And there's no nuance, which is too bad, because that's what we need right now, is we need nuance. Autocorrect. Yeah, there you go. Mike Khalil. I always wondered how light from 13.8 billion years ago reached us now. How did we get here before the light reached us? So the thing that's really important to understand is that the observable universe that we see, the sphere of light that is around us, where the light has taken that 13.8 billion years to get to us, is not the actual universe. It is just a small portion of the actual universe. And so that's why you call it the observable universe. And the way you can sort of think about that, the way I describe it is you're walking in fog, and I've used this term before now, which is that you're walking in fog, and up close to you can see your hands, and then farther away you can sort of just barely see cars and stuff, and then farther away it's just fog. And so that is your local fogiverse, right? That the things that you could see very clearly next to you, I can't see if I'm also trapped in the fog somewhere else. I have my own different fogiverse. And so at the beginning of the universe, shortly after the Big Bang, about 380,000 years after the Big Bang, when the universe finally became transparent, photons of light started to head out into space. And they were able to make it all the way, travel for billions of years, because there was more universe. We may have this observable universe around us, but that is just, there's much more universe around that. And so all of those photons have been just taking that journey for the 13.8 billion years to finally reach your eyeballs. And it is, and that every minute that goes by, new photons that started at the same time have finally completed their journey to reach your eyeballs. And then a minute later, a day later, a year later, the photons that began that journey that much longer have finally arrived to reach your photons. Those photons have finally reached your eyeballs. Pete Rund. Will Vera C. Rubin vitalize the possibility of Planet 9? Vera Rubin is the best tool to find Planet 9, if it exists. And in fact, the time that we're recording this now, we are almost a week of Vera Rubin operations, with it finding about 800,000 objects a night. Interesting alerts. Supernovae, transients, active galactic nuclei, asteroids, comets, and eventually, if it's out there, one of those things will be Planet 9, or Planet 10 if you think Pluto's Planet 9. I don't take a position in this fight. The next planet, because the current crop of telescopes have, and the kinds of all sky scanning that has been done so far has failed to pick it up, which means that it is fainter, smaller, farther than what the current survey telescopes are able to find. But Vera Rubin is just next level. Vera Rubin is an entirely different creature, able to see objects that are much fainter and to track any kind of movement that's going on in the sky. So when will we see it? I mean, I should actually talk to somebody about that. I've got an interview coming up with someone from Vera Rubin. We're going to be talking about the data pipeline side of things. And so maybe he'll know about Planet 9, but maybe I'll just talk to Mike Brown and sort of find out what their plans are to search for Planet 9. But if it's out there and it's possible to find it, Vera Rubin will find it, as well as, 800,000 other things every single night. But one of those could be Planet 9. Festralnice. Could you easily tell what different areas an astronomer, astrophysicist, and cosmologist have? Are there even more specialties that have had space as the research area? There's a lot of overlap between astronomers, astrophysicists, and cosmologists. So, like an astronomer is typically making observations of things that are giving off light. So galaxies, stars, clouds of gas and dust, exoplanets, and they are measuring them and trying to understand their workings. Astrophysicists are trying to understand the forces that are happening with objects out in space. So magnetic fields around neutron stars, black holes, accretion disks, the kinds of places where physics really kind of takes hold of what's going on. Well, like an astronomer can measure the light coming from a galaxy and tell you where the star formation is happening. An astrophysicist might be wanting to specialize in the mechanics of plasma in a star, a newly forming star, and what you would see and what causes the jets to come out of these stars. So they're very similar, and they do very overlapping work. And cosmologists are generally concerned with, say, the Big Bang, with the origins of the universe, but also the large scale structure of the universe, the clusters of galaxies at the largest scales, the nature of dark matter and dark energy, and what influence those have played on the history of the universe. But again, there's a ton of overlap. Plenty of astronomers are thinking a lot about the large scale structure of the universe. So there's a ton of overlap. And then, there are specialties. I would say the main other specialty is planetary scientists. So, a geologist studies the Earth. A planetary scientist studies geology on other planets or atmospheres or water. And so that is something that is like another specialty. When I talk to somebody about Mars or Venus, I'm talking to a planetary scientist usually. Bryce Laughlin, if the universe has no center and every view looks into the past, would most civilizations we see still be frozen in a time before they even evolve forever out of sync with each other? I mean, not exactly, but any other civilization that we see out in the universe, we're going to be seeing them back in time for sure. So, if we see a signal from a civilization, and they're on a planet that is 1,000 light years away from us, then they sent that signal 1,000 years ago. And imagine, right? If we sent out a signal 1,000 years ago and some other civilization picked it up and then replied, or I guess we would have had to have sent it 2,000 years ago. And so think about where humanity was at 2,000 years ago. We send a signal out, take 1,000 years to reach another star system. The star system, the civilization on that star system thought about it for a while, and then they sent the message back to us, and then take another 1,000 years for that message to get back to us. Round trip time of 2,000 years. Things have changed, and so even if we do detect the presence of a civilization out there, it could very well be that we're seeing them as they looked 5,000 years ago, 10,000 years ago, 100,000 years ago, or if we see some expanding sphere of colonization in another galaxy, if we see it in Andromeda, then this happened 2.5 million years ago, which is kind of crazy. And there's an interesting paper that came out today that we reported on Universe Today, where someone did the math and said, okay, based on the fact that we have not detected any signals so far, and that you would expect that if civilizations are very long-lived, then they would go to a bunch of star systems, they'd set up a lot of transmitters, they'd be sending out a lot of signals. We should see signals. And that because we don't see those signals, we can actually calculate the age that civilizations are expected to last. And this is one of the parts of the Drake equation, which is how long will a civilization be communicating for? In other words, how long will a civilization last before it wipes itself out? And according to this paper, the astronomers calculated that it's about 5,000 years. That on average, for us to see the universe that we see and the lack of signals that we see, the universe that civilizations on average should live about 5,000 years before they no longer transmit. You can sort of take that to mean whatever you want. Silas Miller, how powerful could gravitational waves get on Earth? Could we ever feel them and not die? Gravitational waves can never be very powerful this far away. That it required an incomprehensible feat of engineering to be able to even detect them in the first place, where you have the arms of these interferometers, the LIGO and Virgo and Kagra experiments, where you have lasers that are bouncing back and forth along a 10-kilometer long arm, but back and forth, back and forth, back and forth, back and forth, so many times, so that you're essentially getting the length of that arm, but multiple times. And then you're measuring this imperceptible, tiny little distortion in the length of the arm that is telling you that a gravitational wave has passed by. That you would need to be extremely close to the black holes that were colliding for the gravitational waves to cause you any damage. They would, that you would absolutely, like when gravitational waves roll past the Earth, they are expanding and contracting space itself and the matter in the space, in 2 dimensions, 3 dimensions. And so you would be torn apart and then put back together. But, once you've been torn apart, it's really hard to kind of put those pieces back together again. If you're like close enough to a black hole. But there are other forces, intense radiation coming from the black hole environment, the tidal forces of gravity from those black holes. All of this would be very bad. And then you would add the feeling the gravitational waves as sort of insult to injury on top of that. But you'd have to be very, very close. So no, there's nothing close enough to us that could have us feel any kind of damage from the gravitational waves. Just Chris, if the farther away from us, the faster space is expanding, would the perception of us from there be the same? Yeah. So we stand here on the Earth and we look out into space, and except for a couple of rarities, Andromeda and M33 galaxy, the rest of the galaxies in the universe are moving away from us. Isn't that weird? Isn't it weird that they're all moving away from, like, what did we do that all the galaxies want to get away from us? We know what we did. But if you went to any one of those other galaxies, you would also see the same thing. All of the galaxies in the universe are trying to get away from you. And if you go to anywhere, you're going to see the same thing. And so, yeah, if you went out to the other side of the observable universe, you would look back. Our Milky Way would be just cosmic microwave background radiation. It would not have even formed yet. And yet it would still be moving away from you at top speed. Slow Boy Fuel Pump. How devastating would a Carrington event be to our plans for the moon and Mars? I mean, like a Carrington event, this was this thing that happened in the 1800s that was a very powerful solar storm that, I always have to say that it caught the telegraph poles on fire, that you were able to see auroras close to the equator. It was a thing. And that if it happened now, like really any flare that is above 10, like an X10 flare, and there was one of them we had an X8 flare earlier in February. But yeah, an X10 flare is once you start to get damage to the electrical grid, damage to satellites, communications, blackouts on the part of the world that is facing the sun. And those happen fairly often. Every solar cycle you get a few of these X10 flares and above. And this is not the worst that the sun can throw at us. We have seen flares that are worse than the Carrington event. They just went in other directions. They didn't come towards us. They went off into space. But if we were on the receiving end of that flare, it would have been a very bad day. And we have had problems with flares in the past in our more modern age. Like 1989, there was this ice storm in Quebec and there was a solar flare. We had problems with the power grid in Canada. There have been other times when solar flares have caused. There have been other times when solar flares have caused damage on Earth, and so like, what would that do? Well, if there was a spacecraft filled with astronauts that were on their way to Mars and they happened to get caught during something like the Carrington event, they could receive a lethal dose of radiation in an hour, and then they would die within a day. Right. So the the chances of that happening are incredibly remote, but it's not zero. And so there are preventative measures that NASA has proposed to be able to deal with this. Essentially, like for the Artemis mission, for the Orion capsule, the astronauts, if there is a powerful solar flare while they're on their way around the moon with Artemis 2, they have a bunch of supplies on board that they can use to shield themselves. Essentially, they build a fort inside the Orion capsule and they hide inside behind all of their water and their electronics and their food and anything that can put protons between them and the solar flare. But if we have a moon base, that base will need to be shielded. If we have a base on Mars, that base will need to be shielded. People will have to live underground. They have to get a meter of regolith between you and space. And until you do, then you are at risk of damage from solar flares. RP1 for breakfast. More importantly, is my AC unit in danger? Yes, it is. Sorry, just looking. Page Potter, how do astronomers decide what gets observation time when demand exceeds supply? Yeah, one of the cool things about observatories is that they are free to use, that you don't have to pay any money to use any observatories, any of the space observatories. They're all free for anyone in the world. And so if you were an astronomer from, Australia and you want to be able to get time on a NASA space telescope, no problem. All you have to do is make the science case to the committee that approves time on the telescope. And time on the telescopes is extremely limited, that both the Hubble Space Telescope and James Webb, and really a lot of the world's largest observatories, are oversubscribed. So every year, the James Webb group takes in proposals from the scientific community for all of the science that they want to do on James Webb. And then they review all of the proposals and judge them. They say, will they, is this an efficient use of time? What is the science case that is being made? What is the benefit of any interesting science that could come out of this? And that if you're asking for large amounts of time, you're going to have a harder time than if you just want an hour or 20 minutes or 10 seconds of time on James Webb. And then they allocate the time, and they know which objects are going to be visible to James Webb and which things are close to other objects. And so they try to bunch them up so it's going to observe with minimizing the amount of time that has to spend slewing around to different targets. And then they have some discretionary time. So if something exciting happens, like there's a comet discovery or an interstellar object, then they can still make some observations of that thing. And so it comes down to the steering committee, the committee for each one of these telescopes, that sits down, analyzes all the proposals, plans out the year. And in fact, we did a special on Universe Today last year for the sort of major classes, the interesting proposals that were accepted last year. And I think we'll probably do it again. It's going to happen fairly soon. But we're up to 5. I think we're on series 5 of James Webb at this point, which is kind of amazing. We think about how like we are halfway through what James Webb's original operating time was supposed to be. Think about that. Now it looks like it's going to last a lot longer than we had thought, like probably more like 20 years than 10 years. But still, we've actually been using this telescope for quite a while and getting a lot done. Ilya Kuryakin, can even non-scientists apply? Yeah. you don't need to be an accredited astronomer. You don't need to be a professor. You don't need to have a doctorate. Anyone can apply, but you have to make the case that you're not going to waste their time. So if you've been vibe sciencing with ChatGPT and it's giving you a bunch of ideas and now you just want to get some time on the telescope to test those ideas, you're probably not going to make it. But if you have contributed to a lot of scientific papers in the past, you know what you're doing, then anybody and amateur citizen scientists have gotten access to these telescopes as well. So it is theoretically available to anybody who can make the science case to use them. Matt Squirrely, what is it about winter that makes astronomy better? Is it the same for everyone on Earth, or is it true only for colder climate region because in winter there's less pollution? So the big thing that astronomers are looking for is called good seeing. They want minimal amounts of atmospheric disturbance. Now, obviously you don't want any clouds and you don't want light pollution, but once you've dealt with those, then the thing you want is very still, clear skies. And those are best when the air is cold. And so like the best place to put a telescope on Earth is in the mountains in Antarctica. And in fact, there are some telescopes in the mountains in Antarctica, and they're very good. But you also want to be high up. You want to be above as much of the atmosphere as you can. And that's why they put telescopes on the tops of mountains. And so you have less atmosphere above you. You have generally colder atmosphere above you that is stiller and that gives you as good of seeing as possible. What you don't want is like really humid atmosphere and very turbulent. And so you can get, and it's amazing. Like if you do have access to dark skies, I do. I can go out on a night, I can look up and I can just see that it's a bad night. Now there's no clouds in the sky. There's no haze in the sky, but the stars just don't look great. And then every now and then you go outside and the stars are just perfect. It's dark between the stars, and then the stars are these pinpoints of light that aren't moving and wiggling around. And actually, this happened to me about a week ago, and we were having some cold weather, so that was part of it. And I am a little bit on a mountain, but like 250 meters up. It's not much. But there was a fog above the city that is relatively nearby me. And so that was blocking all of the light pollution from that city. And suddenly the stars were perfect. It was the perfect night and so I just stood there looking at the stars just with my eyes for like half an hour. I couldn't believe how beautiful it looked. So it's kind of amazing how much variation. You spend a lot of time outside, and if you do have dark skies, you will see all the different flavors of it. But you want dry air as well. So, desert, mountains. And so that's why when you look at the Atacama Desert in Chile, they are really high, really dry. They're the perfect places to put telescopes. I typograph. If we are alone in the universe, do you think that there are any planets that are habitable for humans? If yes, how can a habitable planet with any life on it look like? So we breathe oxygen, right? And the atmosphere is 21% oxygen. And that is because we have had cyanobacteria and plants producing oxygen for hundreds of millions of years, increasing the amount of free oxygen that's in the atmosphere. That without plants, that oxygen would go back down to very low because the oxygen is very reactive. It wants to get absorbed into rocks. It wants to get absorbed into the ocean. It wants to be sequestered in the inside of the earth with plate tectonics. And so without the life, then we would have other chemicals in our atmosphere, nitrogen, carbon dioxide, but we wouldn't have the same amounts of oxygen. It was called the oxygen catastrophe when plant life first figured this out and started to fill the atmosphere with oxygen. And so we couldn't breathe on a planet that didn't have plant life on it, that didn't have cyanobacteria, that had been pumping out oxygen for hundreds of millions of years, or whatever is the alien version of cyanobacteria. So if there is no life on any other planet out there, then none of those planets are habitable today. You know, it doesn't mean that they would never be habitable. You know, if you have a planet that is in the habitable zone, has liquid water on its surface, it has geology, chemicals, rocks, mud, all of this stuff, sand. It just doesn't have trees and animals and you know, bacteria. And so we could seed that planet with life and come back a few million years later, and it will be on its way to becoming a habitable planet. So there is kind of no such thing as a habitable planet without life on it for us. And in fact, Earth is the most habitable planet in the universe for us, that we evolved in lockstep with the conditions that we find on Earth. Our bodies are tuned to the amount of oxygen that is available to us in the atmosphere. And so any other planet, if it had too much atmosphere, or any other planet, if it had too much oxygen, not enough oxygen, different chemicals in the atmosphere, higher levels of carbon dioxide, you know, higher levels of ammonia, whatever, we would not be able to survive in it. So I would be like, if we did find life on other worlds, you know, it'll take a while for us to find a place that would be habitable for human beings. It's not as common as they make it look in science fiction. Dougal, how often will you be looking at fresh Vera-Rubin data? So I did look, actually someone emailed me and they have tapped into one of the data pipelines, pulled in all the information, and then filtered it for objects that are bright. And by bright, they were looking for things that had higher than magnitude 16, like, yeah, 16 and above. And 16 is, you would need a 150 millimeter telescope with a good camera system to be able to even observe something that faint. It's tough. It's not that you can't do it, but it's tough. So there's going to be a lot of stuff, you know, of the 800 million things, only a handful would actually be visible to someone's telescope, that you could find an asteroid or find a comet or find Planet 9, or find a supernova in a galaxy. That the vast majority of it is just inaccessible to most people with their amateur telescope rigs. But it doesn't mean we shouldn't look. Doesn't mean we shouldn't get excited by the pipeline as it's flowing past. So what I want to do is figure out a way to visualize it. I want to come up with a way to show off what's happening with Vera-Rubin, of these 800,000 things that are being found every night. And eventually it's going to be 7 million things found every night. Can we skim off the top of the really cool stuff? Oh, a supernova went off in that galaxy over there. You could just like stare at the screen and watch, like, oh, supernova. Oh, supernova. Oh, asteroid, right? Planet 9, alien invasion. You can see all that in the Vera-Rubin data. But I'm going to be interviewing someone from the data pipeline team next week. And so this is what I want to find out, the nuts and bolts of it. And so that's why I'm doing a journalism. Flow Mystic, going to take pictures of the lunar eclipse tonight and post them online. I'm going to try and live stream the whole eclipse. Thomas Tarkey, if Plato successfully identifies a few Earth 2.0 candidates, do you think that this would inspire governments to increase astronomy funding? Probably not. I'm always so sad about the Kepler mission because it was so ambitious. This was the telescope that was going to stare at a very small piece of the sky long enough for 3 years to detect a bunch of Earth-sized worlds orbiting around sun-like stars in the habitable zone of their star. And here we are, years later, almost decades later, and we still don't have an answer to that question. We could have, like, if Kepler hadn't lost its reaction wheels, we could have gotten an answer to that question. Plato is our next best hope. But it's not as powerful a telescope as Kepler was. But it is expected to find a couple of Earth-sized worlds orbiting around sun-like stars in the habitable zone. The extremely large telescope should be able to observe planets like that directly orbiting around other stars. So there are tools that are coming that should give us an answer to this question. If all else fails, then we have to wait for the Habitable Worlds Observatory. But that's going to be in the 2040s? Late 2030s, 2040s. Unfortunately, we are still a long way away from finding out. Now, good news, I'm doing an interview with the designer of the Habitable Worlds Observatory in a couple of days. And so I will sort of talk all about what it's going to take for us to be able to find that Earth 2.0. And so that's like the first part, is like, what will it take scientifically for us to be able to find that out? But the response will be what the response always is, which is that some nations invest in science, other nations don't. No matter how interesting the discoveries are, they're not usable in our day-to-day lives. And so there's like just a set amount that nations are able to afford for basic research. And so even if you do find planets orbiting around other stars like our sun in the habitable zone, it'll still just be business as usual. There will be funding, people will do research, we will learn more things, and it'll just keep going on forever and ever and ever. RP1 for breakfast. How does light energy get converted into momentum, such as in a light sail? Right, so light has no mass, but it does have momentum. And so photons of light have momentum. When they strike or when they reflect off of something, they impart a little bit of that momentum to the thing that they bounce off of. And so you can calculate E equals mc squared. And this is how light sails work. And this is sort of like, you can also, like, when you fire, just if you point a flashlight and you are releasing photons from your flashlight, you're actually getting a kick in the opposite direction onto your hand from the thrust of the flashlight. So, but yeah, so, and we know this works. Poe, or is it P-O-E? Poe. I listen to these at work. My question is that if we build an interferometer... Poe. I listen to these at work. My question is that if we build an interferometer array connected between Earth and the moon, could it work? So it depends on the wavelength that you want to use your interferometer with. Radio waves, absolutely. And in fact, people are now planning extensions to the Event Horizon Telescope, which is this worldwide network of telescopes on Earth, that they would put telescopes in space, and then they would have atomic clocks on those telescopes, and they would gather information about the event horizon of a black hole, and they would add that data to the Event Horizon Telescope. And if you put your telescopes in space, or you put your telescope on the moon, you are now getting a telescope that is the size of the distance between the Earth and the moon, right? Almost 400,000 kilometers. That is a very big telescope. You're getting that baseline, you're getting that resolution. But if you want to go into other wavelengths, you have to remember, you always have to align the telescopes to the exact wavelength. So we think about, whatever regular visible light is, several 500 nanometers, right? So you have to have them within 500 nanometers of each other, right? You have to know the position of the telescopes within 500 nanometers of each other. which is really hard when you're all the way at the moon. And the moon is moving, and the Earth is moving, and the Earth is rotating. So it is impossible to line those up. You could put two telescopes out in space that are free floating and then have a laser that is communicating between them, that is negotiating the distance between the satellites. And that's what the LISA array is going to do. You can have these three satellites that are orbiting in a triangle, and they are firing lasers at each other, and they are more than 10,000 kilometers apart. And they are constantly measuring their position and using that to measure as gravitational waves sweep past them. And the second that one of them is pulled a little bit out of the formation by the gravitational waves, they will detect it. So interferometers are awesome, but they are really tricky. And so we need to start with building an interferometer that is, 10 meters apart in space, just floating, and then work our way up from there. Thomas Starkey, what kind of capacity would we get if we put the extremely large telescope into the solar gravitational lens? I don't know how much more value you would get by putting a very large telescope to the solar gravitational lens. I should talk to Slava Turshev about this next time I interview him. It's, the sun is doing the heavy lifting. The gravity of the sun is what is doing most of the magnification. And so the size of the telescope that you put at the solar gravitational lens doesn't really matter. You need the minimum size to be able to observe all the way from you to 550 astronomical units to the sun. And so that's why like a 1 meter telescope will do the trick. But really what you want to know is if I make the sun more massive, if I make the sun twice as massive, now we're talking. Now we're making a better telescope. Domingo Flave. Domingo of Lave? Domingo of Lave. Or is it Domingo Flave? What is your favorite wavelength that we study the universe in? I don't have a favorite wavelength. So I think I have reasons why I think they're very cool, all very cool. Like obviously the visible wavelength, those are the ones that we see with our own eyes. And so telescopes are magnifiers of what we can see with our own eyes. And so when you look through a telescope, you're just making your eyes bigger. And that is very satisfying. It's very accessible. We understand it. Infrared, we're seeing heat. And when you look at infrared cameras, you can't see the heat. But when you look at an infrared camera, then you are actually seeing the heat that's giving off, like different wavelengths of light. And you can see how like a person could be running in the complete darkness and yet they were giving off heat. And so you can see them. And that's what James Webb is looking at, is the heat of things, which is kind of crazy. Ultraviolet is cool. That is the sort of where a lot of activity is happening. Star formation, the areas around supermassive black holes, X-rays, gamma rays are pretty cool. Someone said that if you could see the universe as it truly looked, then the universe would look brightest in gamma radiation, because all of the interstellar gas is hot and giving off X-rays. Sorry. If you could see the universe as it truly looked, you would want to have X-ray eyes, because, there is interstellar gas, intergalactic gas. Like the amount of gas in the halo around a galaxy matches the mass of the galaxy itself. And that is all glowing in X-rays. And so if you really want to see the universe, you would really want to see X-rays. So if I had to pick, it would probably be X-rays. Forkrunner, is our universe the result of a black hole exploding? Where does all that matter inside a black hole go in the end? So we don't know where the universe came from, and people have proposed that we are the result of a black hole exploding, but it's very hard to make a black hole explode. That the only way to get rid of a black hole that we know of is for black holes to evaporate, and this is a process that is very slow. It takes a very long time. And you need a time when there's really no energy, no light, no matter, nothing can go into black holes. They're very, very cold, or the universe is very, very cold, and then they will start to evaporate. They'll give off heat. And you'll have these particles that are leaving the black hole, and it's like 10 to the power of 67 years. So 1 followed by 67 zeros is the amount of years it would take for just a stellar mass black hole. And then it's like 10 to the power of 100 years. A Google years is what it would take for a supermassive black hole to fully evaporate. But when the black hole is almost out of mass, as it evaporates, it gets lower and lower in mass, and its temperature rises. And eventually, within the last few minutes, the temperature gets so hot that it explodes in this blast of gamma radiation. And astronomers have actually looked for this. They've actually looked out into the universe to see if they can find black holes, primordial black holes exploding because they have finally evaporated. We haven't seen any, but theoretically they are out there. And so this idea that where does all that stuff go? Well, it just gets added to the mass of the black hole, and then when the black hole stops feeding, then it slowly evaporates it all off again. So think about, I don't know, if you go out in the rain and your clothes absorb a bunch of rain, and then when it stops raining, your clothes will start to evaporate that water off of your clothes, and eventually you'll be dry again. You'll be miserable, but you'll be dry. Or you'll be cold, but you'll be dry. And so that's what's happening with black holes. And so it doesn't look like some kind of mechanism where a black hole will just gather a bunch of material and then it'll get to this point where it explodes. That there is no limit. A black hole can consume as much as it wants, right? As long as you're willing to keep feeding a black hole, it will take it. It's only when you stop feeding it that you actually get a chance for a black hole to explode. And only when they finally reach the end of their life and they've almost already completely disappeared. That's when they explode. Josh Miller, is Vera Rubin currently scanning in the direction that we suspect Planet 9 might be? Well, Vera Rubin is scanning in all the directions. Vera Rubin is taking a full image of the entire southern sky every 3 days, just relentlessly, night after night after night. Take a picture, 15 seconds, take a picture, 15 seconds, take a picture. It does the whole sky. So is it scanning the direction that we suspect Planet 9 might be? Yes. Because Planet 9 could be anywhere in the sky and Vera Rubin is going to catch it. Now, that's not entirely accurate because Vera Rubin is positioned in the southern sky. It's down in, it's in Chile. And so it can only see the sky that is visible from its perspective. But it has a really good view of the plane of the ecliptic. That is sort of where in the sky all of the planets are bunched up. And so it's expected that, if all of the planets have been found in this very thin band in the sky, that Planet 9 will be there too. Now, other objects have been found on extremely highly inclined orbits like Eris. Eris is at like a 44-degree tilt from the rest of the solar system. Even Pluto is like 17%. So it's pretty highly tilted. But the safe bet is that Planet 9 will be in the plane of the ecliptic, especially if it's big, because it would have formed out of the protoplanetary disk with all the rest of the planets, and so it would be orbiting like the rest of the planets are. And so that's where you start. And the ecliptic is well positioned in the sky for Vera Rubin. And so it will be scanning that and even putting a little extra emphasis on that region because there's most of the asteroids, most of the comets, dwarf planets, they're all going to be in this thin band in the sky. And when new telescopes are developed, the sort of power move that astronomers make is they scan the ecliptic because that's where you're likely going to find things. So when the Very Large Telescope was built, astronomers used it very quickly to find Eris, Haumea, Makemake, Sedna, all of these various large Kuiper-built objects, all these dwarf planets were all found because you had a more powerful telescope. You scan the area where you know the planets are, or you know where all the things are likely to be, and you'll find stuff. And so that is the region of the sky that Vera Rubin is probably going to find things. And it is, you know, that it's very well positioned to be able to find that. Ed Skeptic, if we had a powerful enough telescope, could we actually see moving things on a planet 50 light years away? I mean, actually going about their business. Of course, theoretically, I mean, the laws of physics don't prevent you from being able to see things that are very, very far away and very, very small. Phil Plait actually just wrote a post on for his newsletter where he calculated what kind of a telescope would be required for aliens to see dinosaurs on Earth from, I forget the distance, like 1,000 light years away or something like that. And he calculated that it was a telescope that was tens of light years across, right? Like it would be ridiculous. Like, it is beyond our ability to build a telescope that big. So theoretically, yes. Practically, no. So you're saying there's a chance. Ragetail, when they say the farthest galaxy we can see is 13 billion light years away and say it's basically right after the Big Bang, what would Earth 4 billion years ago have seen there? So the important thing to think about here is that when you see the cosmic microwave background radiation, which is like the first light that could reach out into space, and you are seeing the light as it left that place 13.8 billion years ago, that is a snapshot in time of this one region of the universe, this sort of shell around us. And the light was released, has been traveling for 13.8 billion years, and the universe has been expanding, and the light has finally reached your eyes. You know, you see the light in one direction, you see the light in the other direction. That light is getting to you at this point. And so if you were on Earth 4 billion years ago, then your cosmic microwave background radiation would be 9.8 billion years of time, that you would be seeing stuff that was 9.8 billion years ago. And it would be different stuff. Like, it would be a different part of the universe, because that this sort of sphere of light that is being emitted towards you has gotten bigger. And so 4 billion years ago, the universe is much smaller, and you're seeing stuff that the light has only been traveling for just shy of 10 billion years. And it's different places, different galaxies, different spots in the sky, totally different. Now it looks kind of the same. You're seeing kind of blobs of over and under density in the cosmic microwave background radiation, but it is totally different places in the universe than what we're seeing today. And even like every second that goes by, you are seeing a different part of the universe. Every minute that goes by, you're seeing a different part of the universe. So think about like the size of a galaxy, right? The Milky Way is 100,000 light years across. And so that if you waited 100,000 years, you would see a galaxy's worth of width of new space out there. And you'd be seeing stuff, you know, if at the beginning, if there actually was a Milky Way galaxy, which there wouldn't be, right? Because it's early on in the universe. But if there was, then at the beginning of 100,000 years, you'd see the front end of the light from the galaxy hitting you. And then 100,000 years later, you would see the light from the back end of the galaxy finally reaching your eyes. But that analogy doesn't hold. I need a better analogy, because that one doesn't work, because, you know, there weren't galaxies back then. There was just clouds of hot hydrogen. Stephen Hopkinson, if I was an alien, what would you ask me? I mean, I would have so many questions. Like, I want to know all about your culture, all about your science, all about your history, all about your biology, all about how you interact with each other, your society, your your media. I would want to know sort of, did you suffer the same kinds of wars and conquest and things that we had in our history? And then I would love to know how you made the trip. How'd you get here? What'd you use? What's the tech? So I would have so many questions. I would have we would have like my question shows, but you would have to be the person answering the questions and they would just go on forever. Perry M. The closest G star to us is Tau Ceti at 11.9 years. Is that a good candidate for Vera Rubin to find terrestrial world close to us in a stable star system? Unfortunately, Vera Rubin is not good for that kind of thing. Theoretically, Vera Rubin can help find exoplanets because it's looking for changes. And so it's going to see dimming of stars and then brightening of stars, and that you could then correlate that to planets passing in front of stars. But it's going to take more detective work to be able to figure that out. But it is just not the best machine to be able to find that. The one you probably want is the Plato telescope, which is going to be a mission launched by the European Space Agency in about 3 years from now. 2 years, 2028. Yeah. And so if there is a planet that is aligned in front of the star from our perspective, is passing in front of the star, right? Then and blocking the light of the star, then and only 11.9 light years away, that's very close, then Plato probably would be able to spot it. But if that was already there, I mean, people have done surveys for planets around the closest stars. TESS is doing it right now. And if there was one there, we probably would have noticed. Like, we found a planet at Proxima Centauri, multiple planets at Proxima Centauri, and it's a red dwarf. So, but it would be amazing. Right? The closer the planet, the better, because then our biggest telescopes can try to examine them. Swat Orsdemirsi. Does it bother you that we're living on the brink of radical technological advancements in space and that your life might end before you get to see them? Feel like you were born at the wrong time? I think that we will always feel like we were born at the wrong time. My father watched the Apollo landings in 1969, and he was an adult at the time. And there are people who are watching this live stream right now. You were children, or maybe adults, but you were children when you watched the Apollo landings happen. And I'm sure you felt like, this is incredible. Like, we are now at this new age of technological advancement. And then you had to wait another 50 years for there to be another attempt on the moon landings. And so there are a lot of technological wonders. I mean, I can sort of think about my life, my professional life, my adult life kind of matched the internet, the World Wide Web. I graduated high school in 1989. I first surfed the web in 1994. Although I was using other internet stuff in like 1992, like Usenet and stuff. And then I started building websites in 1995, and have been doing it continuously since then. And you always felt like, okay, like, this is it. Like, we are now reaching this incredible time in human technology. And yet it sort of advanced more slowly. But then stuff did show up. You got better internet. We got broadband instead of dialing up on a modem. We got cell phones, smartphones. And most recently, we've got ChatGPT, AI, Claude Code. Like nothing has felt like you're seeing the future or feeling the sort of the threat of the future than this sort of modern age of AI. And a lot of the interesting stuff that I'm excited about, obviously, are going to happen in the future. The Habitable Worlds Observatory in the 2040s, missions to Mars, a permanent habitation on the moon. All this stuff is decades away. And, I'm not a young man now. I'm in my 50s. I was 29 when I started universe today. 28? Yeah. Now I'm in my 50s. And yet I've been here for a bunch of stuff. I was here for the discovery of the first exoplanet. I was here for the launch of the Hubble Space Telescope, James Webb, the launch of all of the rovers to Mars. So I think, we will always live in this time where there are incredible technological advancements and we're excited, and we will always feel this grief for a future that we will not experience. And that's the way I describe it. Like, for me, it is grief that I won't see the future that will happen. I won't see us head off to the nearest star system. I won't see that unless, like, obviously when I get my robot body, then everything is going to be fine and I will be there for that. But if I don't, then I do feel sad for sure about a future that I will never see, because I love the future. I think stuff is cool and I want to see it, and I'm curious. I have questions. I want to see answers. So yeah, I feel sad. One of them mine rocks. If dark energy is causing the universe to expand at an accelerating rate, what does this imply for the ultimate fate of galaxies that are currently bound by gravity? So if they're actually bound by gravity, in that if they're within about 5 million light years of each other, that is actually bound by gravity, and that those galaxies will get closer and closer together and they will merge into giant elliptical galaxies. The big spirals will spin into each other. The smaller dwarf galaxies will merge in with them, and you'll get these just big old blobs of stars. But if it's beyond about 5 million light years away, then the expansion of the universe and the acceleration of dark energy are stronger. And so those galaxies are going to be torn apart. And you can sort of imagine at a local level, galaxies that are kind of close together are starting to clump together. But then clumps of galaxies are spreading apart from each other. And eventually they will fall over the cosmic horizon. So in just about 100 billion years from now, we would look out into the cosmos and we would not see any other galaxies easily. Their signals will always be there, but essentially all of the galaxies will fall over the cosmic horizon from our perspective. So what is the fate, right? The fate of them is that, so like the galaxies that are bound together by gravity will merge into this giant elliptical galaxy, and then the interactions between the stars will kick out stars one at a time. They'll just be thrown out into space. And eventually, and all of the stars will lose all their planets. So this is kind of interesting. So in about 10 billion years from now, just the gravitational interactions between the other stars in the Milky Way will pluck away all of the planets from the solar system one by one. You'll be left with just Mercury, probably. The sun and Mercury. And then Mercury will probably remain with the sun. But then Mercury will have been destroyed by the sun because of the red giant phase. So, there will probably be no stars. So anyway, in that long history, all the stars will eventually be kicked out of the galaxy. All of the planets will be kicked out of the star systems. You'll just be left with the black hole, the supermassive black hole at the heart of the Milky Way. That will be the Milky Way. And so you will end up with free floating stars that are separated by enormous distances in space, falling over the cosmic horizons from each other, and the supermassive black holes that are the final remnants of what were once galaxies. That is the ultimate fate. IOI. Alien Space just posted a Dr. Zubrin interview. You have to be able to get him. He's the ultimate first principles contrarian. When is your Zubrin pod? So I've interviewed Robert Zubrin many times. So if you want to do a search on my channel, you probably will find it. And he's a good time. He is definitely a cranky man. You have to get him on a good day. And he doesn't have a lot of patience for anything that isn't sending spacecraft to Mars and one way, ideally, Mars or bust. So, yeah. No, Zubrin's great. The Case for Mars, his book, was one of the influences, probably the main influence for me to get involved in the channel, in being a space journalist, in just being, writing about space and following space exploration. Like when I read The Case for Mars, I became a true believer at that moment. I'm like, yeah, we should live on Mars. I'm in. I'm going to dedicate my entire life to making that happen. Here I am now, 27 years later, kind of going, I don't think we should live on Mars. But yeah, super influential. And yeah, I've interviewed him many times. Where are we at? Whoa, 650. Lubo in China. Is there a gravitational limit of a planet to radically reduce the chance of a civilization to leave its own planet? Is the Earth just perfect for planes and rockets? There is a theoretical gravitational limit, and that is that the amount of fuel or propellant and energy required for you to be able to leave your planet exceeds the mass of your planet, right? That if you've constantly got sunlight that is falling on your planet, you've got energy coming, and then you need some kind of propellant. And so if you use up every kind of propellant on your planet and you build a gigantic rocket and then you use that to try and get off the planet, that is the limit. And it's kind of surprising how much more massive of a planet you could still build a rocket. There was someone did the calculations, and I don't remember the exact numbers. I should redo them, but that if you had a planet that had, say, twice Earth gravity, you could probably still launch a rocket. Now, the payload that you would get into space, you would need a Saturn V rocket, and you would be able to get just a couple of 100 kilograms into space. It would be tough, but you could still do it. So Earth is very lucky in that we have a thick atmosphere, a habitable planet, and yet we do have a weak enough gravity that we can build rockets that can launch tens of thousands of kilograms into orbit. And that if the gravity well was bigger, then we would have a harder time being able to launch rockets. But it's not impossible. And so, once you get to 3 Earth gravity, then you're starting to sort of think about how you're going to use all of the propellant on your entire planet to be able to pull this off. And then you get like 10 Earth gravity, you would need all of the matter in the universe to be your propellant, right? Like the rocket equation gets complicated fast. But I do sort of imagine there will be this time, or I sort of think in sadness that there will be this time when we run across this planet where there's an intelligent life forms down at the bottom of a gravity well that is so strong that nobody would be willing to go down it to rescue them, that there's no way to get back, that if you go into that gravity well, you're never coming out. And so they may be able to participate in the Galactic Federation. They're going to send messages. They're going to watch our media. They're going to think big ideas, but they are trapped at the bottom of their gravity well forever, and they can never get out. That's sad. We would like fly by and we're like, sorry, the one thing we can't do is bring you to space. But if you can get anything into space, like even if you do have to build a Saturn V rocket and then you can only get a couple 100 kilograms into space, that's a bootstrap, right? Then you go off and you find an asteroid and you turn that asteroid into something more, and you can sort of find your way up. You can climb the ladder to get out of your gravity well. But if it's more than that, you're just stuck. Just looking at the last question. Che Weaver, if the universe started at a single point and then expanded in every direction at the same or close to the same rate, then doesn't that mean that there exists a theoretical center of the universe? So that is a misunderstanding. that the universe was, if the universe is infinite now, then the universe was infinite at the moment of the Big Bang. That it would still went on forever. That the observable universe that we see does have a center. It's you, right? The fogiverse, if you're standing in the fog and you see your hand clearly, you're at the center of the fogiverse. And when I am over tens of meters away from you in a thick fog, I can see my area around me, but I can't see you very well. I'm in my own fogiverse. But there is more verse around both of us, right? So you could say, well, wait a minute. Like, isn't the fact that you're in the fogiverse and you can see your hand, doesn't that mean that you are the center of the universe? You're like, nope. You're only the center of your own personal fogiverse. Other people are the centers of their fogiverses. And so you are the center of the observable universe. I am at the center of my observable universe. But there is more universe. There was more universe at the beginning of the universe, and there's more universe now than what we can see. And so people always imagine that there was this primordial, this primeval atom. And like, there's terrible descriptions of this, right? If you go and watch some science documentary, like astronomers say that there was this primeval atom, this singularity that from out of which the entire universe came. Like, nope, fail, right? It wasn't a singularity. Whatever it was had the same kinds of topography as the universe has today. That if it's infinite now, it was infinite then. Just that the things in that infinite universe were more dense, closer to each other. And so you don't have this flip from a singularity, from an atom to an infinite universe. Like that doesn't, like if that feels like it doesn't make sense, good, right? Because it doesn't make sense. You have to, it's infinite then, infinite now. Or maybe it was finite then and finite now, but you don't go from finite to infinite. All right. I think we've reached the end of this week's episode. So, but I will try. I'm going to do some technology tests shortly, and I'm going to try to live stream the eclipse tonight. We'll see what happens. I give myself a 50-50 chance of being able to pull it off, or just sleeping through it, because 3:30 in the morning, this is not right. But I don't have anything big to do tomorrow, so maybe I'll just sleep. Anyway, a huge thank you to all of the moderators who joined us tonight. Zapfan, I saw you there. I hope you're enjoying your sort of less responsibility. Now you just get to enjoy the show and enjoy chatting with other people. Thanks in advance to Chad and Anton. They're going to have to watch this nonsense and edit it down into some kind of cohesive video. We've got something crazy that Anton just did. And I don't even want to tell you about it yet, but we will drop it probably this weekend, and hopefully it'll blow your mind. Yeah. So stay tuned for something that I think is going to blow your mind. And I don't want to spoil any more of it. So, all right. We will see all of you next week. Thanks, everyone.